Welcome to the Insightful Professor. Today we're going to do a short presentation on data representation, how computers represent data. First, what we want to consider, though, is how do people deal with data? In particular, the type of data most commonly used or encountered would be simple text and numbers. Concept of other types of data like video and so forth, it goes along the same idea, but we'll just focus for quick illustration the concept of how numeric data would be represented and how character or textual data would be represented. Now, people use the 10 decimal digits for numeric values, 0, 1, 2, 3, up to 9. So examples might be 5,280 to indicate the number of feet in a mile, or 12 to indicate the number of eggs in a dozen. We typically use the 26 letters of the Roman alphabet for dealing with textual data. So we have A, B, C, all the way up to Z. Now, we also make a distinction when working with the characters of the textual data between uppercase and lowercase. So we're going to have to take that into account when we discuss how the computer is going to deal with representing textual data. So a question comes up then. How do computers represent the numeric and textual data? We just talked about the concept of how people deal with it. When we interact with a computer, we're dealing with what might be considered an external representation of data. What we type on the screen or the characters we see on the keyboard, these are using our system of representation, but that's not what the computer deals with. See, the computer allows us to interact with it by defining an interface that can accept the decimal digits and the Roman letters of the alphabet, because that's what we're comfortable with. But internally, it doesn't represent an A as an A, or a question mark as a question mark, or 9 as a 9. It uses what's called the binary representation, using what's called a binary numbering system. So this is an internal representation, quite different than what is exposed to us through the interface or displayed on the terminal. So if we're saying it uses the binary number system, I suppose we should define what a numbering system is. We say a numbering system allows for us to represent large numbers that are built upon or constructed from sequences of smaller numbers. So consider the number 175 in the decimal numbering system. Each digit assumes a value that's determined by the position that digit occupies within a number. So for example, 175 is 1 times 100 plus 7 times 10 plus 5 times 1. The 100, the 10, and the 1 are based upon the positions that the digits 1, 7, and 5 occupy, respectively. So all numbers in a numbering system are constructed with a fixed set of digits. In decimal, we deal with the digits 0, 1, 2, 3, up to 9. Because there are 10 digits, we call this base 10, and we also refer to it as the decimal system. Now, how's a number evaluated? Well, we pretty much went over that, but here's a quick little idea. What happens is each of the positions, for example, when we came up with 10, 100, 1 as the values for the positions, we didn't pull those numbers out of the air, but each one of the positions represents that base, which in the decimal number system is 10, raised to some power. So the 1 is in a position that is 10 to the second. The 7 is in the position valued at 10 to the 1. And finally, the 5 is in the position of 10 to the 0. And any base, when we raise that base to 0, always evaluates to 1. And we'll see that holds true for our binary number system as well. So the general rule that we have for trying to evaluate a number is take the base, such as 10 for decimal, raise it to a power of 0, and that gives us the value of any of the 10 digits that we put in that position. Base raised to 1, that's what we have for the representation here. This position would be, in the case of 10, it's 10 to the 1, and that's going to be 10. The base raised to the power of 1 is the base. The base times the base is base squared. Base times base times base is base cubed, and so forth. And we represent that concept on the next page. So our next slide kind of summarizes how we assign the positions. Now, we just talked about decimal where the base is 10. In binary, we're going to see the base is 2. So to figure out the value of each position, simply take 2, the base, raise it to 0, 2 raised to 1, 2 raised to 2, and so forth. If you had base 8 octal, it would be 8 raised to 0, 8 to 1, 8 to the second power, 8 to the third power, and so on. So there's no trick to this. It's pretty straightforward. But there's a comfort level. Obviously, we've been working with decimal for a long time. Binary, octal, hexadecimal, other number systems used by computers. It takes a little time to get used to them, but the principle is the same. So that makes it a little easier. You just have to put different values for your base. So let's take a closer look at the binary number system. In the binary numbering system, we're working with what's called base 2 as opposed to base 10 in our decimal system. So we have only 2 digits rather than the 10 that we saw with decimal. The 2 digits are simply 0 and 1. You'll notice that when we worked with 10, base 10, the highest number was 9. It's 1 lower than the base. Here, the highest number is 1, which again is 1 lower than the base of 2. But we only have 2 digits, so that should be pretty simple. Each binary digit is called a bit. Bit is actually an abbreviation for binary digit. Like the counterparts in the decimal system, the binary digits, or these digits, will occupy positions within the binary number. The positions are, again, the base raised to the power of 0, 1, 2, and so forth. What I've done here is I've shown you the base raised to the power, and beneath it I've shown you the decimal equivalent to make it a little easier to understand the value of each position, because we're probably transitioning from decimal to binary. So here we go, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the second, which is 2 times 2, is 4, 2 to the third, which is 2 times 2 times 2, is 8, and so forth. When we deal with an 8-digit binary number, take a look at what I'm showing here. We go all the way up to 2 to the 7th, or 128. Now, let's look at the representation using this scheme. We were working with a number of 175 in decimal. The equivalent in binary of this very same number is what I'm showing here. Notice it's consisting only of 1s and 0s. Those are the only digits available to us in binary. The number 1, 0, 1, 0, 1, 1, 1, 1 is 175 in decimal, but this is how we express it in binary. So how did we come up with this? Well, if you look at 175, you can think of, well, it has a value of 128 in it, right? So if you subtract the 128, the first thing you do is denote that there is a 128 by putting a 1 in the position, subtract the 128 from 175, and what do you come up with? Well, you come up with a number that is going to be considerably smaller. Subtract 64? You can't. So when we come to 2 to the 6th, or the 64 position, we put a value of 0 in there because there are no 64s. So we continue on, and now can we subtract 32? Yes, we can. So subtract 32 from our number. Note that we used a 32. We reduce the number. Then can we subtract 16? No, not big enough. And we keep going and going and going. And for each position where we can subtract, we'll reduce the number that we're dealing with. The original decimal value is getting reduced by the value of the binary position, and we note that we have used one of those, and we mark it as 1. And again, if the number that we have is such that you can't take out a 16 or a 64 or whatever, we denote 0 in the corresponding binary position. So take a look at it and confirm it for your own understanding. 175 consists of 1 instance of 2 to the 7th plus 1 of 2 to the 8th, or I'm sorry, 2 to the 5th, and so on, which is 128 plus 32 plus 8 plus 4 plus 2 plus 1, and that should give you the 175 if we've done this correctly. Now, how do you represent characters? Well, characters use the concept that we just looked at for the numeric values, the binary, except what we have to be assured of is if I'm going to represent the uppercase A, then each time I represent it, it has to be the exact same numeric value. We want this consistency. Otherwise, it's random, and we won't be able to figure out what the character is, nor will a computer be able to figure it out. So what we need is some kind of a standard code that says this numeric value maps to this particular symbol or character. These are referred to as character codes. And over the years, computer systems have adopted a variety of different character codes. There's something called IPSIDIC, there's something called BCD, there's something called ASCII, and Unicode, and so forth. Number of different systems. The one that's been standardized for use with PCs, such as desktops, laptops, servers, and then even going into things like tablets and your smartphones and so forth, that is ASCII, ASCII, which stands for the American Standard Code for Information Interchange. A lot easier to say ASCII. The code uses 8 bits to represent a single character or symbol. The 8 bits then give us 2 to the 8, or 256 different possible symbols that we can represent. So that's going to cover, if you think about it, we have 26 letters, uppercase, 26 letters lowercase, and then we've got the 10 decimal digits, and then scan your keyboard. You've got special characters such as exclamation mark, period, comma, semicolon, pound sign, left parentheses, right parentheses, and so forth. And we have plenty of room to spare using the Roman alphabet and the various symbols that we need. Another code to be aware of is something called Unicode. Unicode includes the 256 ASCII numbers, plus it includes many more, which allows us to deal with multinational systems. So if we're dealing with, say, Japanese katakana, for example, we're going to have more than the characters that we have in our Roman alphabet. Or if we're looking for a representation for Chinese characters, Zhongguozi, then what we need is the ability to represent much more than 128 or 256 characters. So Unicode is a multi-byte character system. It doesn't use a single byte, it uses more than one byte, and it's used very often in international and multinational systems. But the principles are essentially the same. Now let's look at how ASCII works. Each character or symbol is associated with exactly one numeric value. The numeric value has to be unique, so we always associate the same number with the same character or symbol. Each numeric value is an 8-bit binary number. Again, using ASCII, it's just 8 bits. For example, if we look at the uppercase letters of the Roman alphabet, the uppercase A has this particular code, 0100, 0001. Uppercase B has this code, C this code, and all the way down to uppercase Z. But remember, we have to account for lowercase as well. So what we see is the lowercase letters, A, B, C, and so forth, have these codes. And additionally, we need to deal with binary numbers for special characters. And here's a few of the special characters. But again, scan your keyboard and you'll see many more characters that we need to be able to represent. So each one has a unique or distinct binary number code associated with it. And that's the notion of ASCII. So if we were to type in a bunch of characters on the screen, we could think of the system as doing this. Because each character on the keyboard has a character or symbol associated with it. Scan your keyboard and you see, oh, there's the key with the A, there's the key with the J, there's the key with the 9, and so forth. When you press a key on the keyboard, the value that is used internally by the computer is a binary number taken from that ASCII code. And the binary number maps to the character that we see on the key. So it's kind of like looking up in a table. Here's the character, here's the number, and the system looks it up in that way. Then what happens is when the system says, now I have to display on the screen something that I've stored in memory, so I've got to print out so people can read this, it kind of looks at, here's the number, and then it goes in the ASCII table and finds the character. And that character is somehow rendered and presented on the screen. Same principle applies if we were to print it out on a printer. So it's doing that kind of a lookup. So that's the basic idea and how we represent data and how the computer then can understand what we deal with and we can understand what the computer deals with. And that's pretty much the idea. Now, a couple final comments here. The ASCII code uses an 8-bit or number or 8-digit binary number to represent a single character or symbol. In computer terminology, 8 consecutive bits is referred to as what's called a byte. And the byte is a unit of memory that we can assign some meaning to. That is, it can represent a particular character, or perhaps it can store some kind of a number that we're going to do arithmetic with. Very often we'll use strings of bytes together. We very infrequently operate on just one byte at a time because we've got a lot of data to deal with. And we're going to deal with much larger numbers too, so we need to string bytes together. But the byte is essentially the smallest unit of addressable memory in the computer, and it contains typically some kind of a symbol when we're talking about interaction with computers and humans. So when measuring the amount of memory that a computer has, or the amount of capacity, say for a disk drive, we use byte as our kind of yardstick or unit of measure. But we don't talk about, oh, it has 2 bytes or it has 20 bytes. We're talking about much larger quantities. So I've given you a few more terms to kind of chew on here. Megabyte. Megabyte refers to millions of bytes. Gigabyte refers to billions of bytes. Terabytes refers to trillions of bytes. So when we're talking about today's computers, we might be talking about so many megabytes of memory or so many megabytes of capacity for some kind of a flash drive or disk drive. But very often we're probably talking more like gigabytes, billions of bytes, or terabytes, trillions of bytes. And again, it's just a compilation of that simple idea of looking at a bit to represent a single 0 or 1, stringing them together to come up with a unit we call a byte, and then stringing those bytes together to give us usable memory. And that's kind of the big overview, high-level overview of how the computer deals with representing data. So I hope you liked this, you enjoyed it, and found it useful. And if you have any comments, let us know. We'll be glad to get back to you. And once again, thanks for watching.